last century, quantum field theory has proved to be the single most sweeping and most successful physical theory ever invented. We can call it as an umbrella term that encompasses many areas of fundamental physics. In this video, we are going to take a tour in understanding quantum field theory, keeping apart the complex mathematics for another video. We would be learning the fundamentals of quantum field theory, why and how it emerged, and most importantly, the actual need for this theory and some of its deep underlying implications. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this fresh new episode on an introduction to quantum field theory. So let us quickly look into what are the topics that we are covering today. Well, there are quite a number of topics. First, we will understand what is quantum field theory. Why at all do we need a unified field theory? Quantum field theory, we need to understand a basic brief history. The classical era, the emergence of the concept of field. Then came the quantum era. And why do we need quantum field theory? There was a problem underlying with Schrodinger's equation. What is spontaneous emission? What is quantum electrodynamics and quantum chromodynamics? What is QED and Richard Feynman's diagrams? The contribution, the problems with infinities, the arrival of S-matrix theory and the problems that persisted, the renormalization method, and Feynman path integration and formulation. These are not an exhaustive topic, but for this video, I think these are the topics which are most important and serves as a basic understanding when we start learning quantum field theory. Okay, so the first topic that comes in is that if you really wonder that what we are actually made of, say for example, you probably would just tell that we are made up of red blood cells or bones or maybe white blood cells, and that is quite good, fair enough. We know that human body are made of these things. And now the thing is that what are those red blood cells are made of? And maybe they are made of certain amount of molecules. And if I ask you what are those molecules made of, you will say that these are made up of atoms which contains proton, neutrons, etc. And what these atoms are made of, and we know that they are made up of quarks, up quark and down quark and things like that. Now, if you say that these quarks, what are they made of? Now, because that have traditionally been considered to be the end of the line, but what are those quarks made of? We can say that these are made up of mysterious entities like substances which we call quantum fields. Now, this is as far as we know a basic understanding of human body or a basic understanding of human nature. Okay, so these invisible fields which we just saw in the figure, we can call it as a quantum field. We will come more about this. They can interact with each other. They can even, some of them flow right through us. Some of them behave like waves. Some of them behave like particles. Some of them can interact with each other. And some of them keep flowing within everything. It is permeable, everything. Now, in some cases, it makes predictions that agree with the experiments, astonishing to 12 decimal places. On top of that, quantum field theory has been shedding enormous light in answering some of the fundamental questions in pure mathematics, especially in the study of four-dimensional shapes and even higher dimensional shapes. So, the theory of quantum fields is arguably the most successful scientific theory that we learn, and that is what we are going to learn. So, this is what the introduction is about quantum field theory. So, what I can tell about, quantum theory is that in theoretical physics, quantum field theory is a theoretical framework that combines classical field theory, special relativity, and quantum mechanics. Together makes up a quantum field theory. So, quantum field theory actually treats particles as excited states, which we sometimes call as quanta, right? Higher energy than the ground state, and which are more fundamental than the particles. The equation of motion that we will see of the particle is determined by minimizing the Lagrangian, a functional field associated with the particle, and interactions between particles are interactions between particles are described by interaction in terms of the Lagrangian involved. Each interaction can be visually represented by, we will see soon, the beautiful Feynman diagrams according to the perturbation theory in quantum mechanics. So this is all I mean to say in a nutshell before we go ahead, so that the curiosity is satisfied that what is quantum field theory. It is something which is combining classical field theory, special relativity and quantum mechanics, and it deals in quanta, the excited states of atoms or subatomic particles. It minimizes the Lagrangian equation of motion and the pictorial representation of subatomic particles. The question is that why do we need a unified theory? And that is what we are coming up in the next part of the video, where I will try to answer it in a very simple terms, the need for a unified theory. So here it comes. Why do we need a unified theory? Now, if you look into something like classical mechanics, classical physics, which starts with Sir Isaac Newton, it actually behaves, or it actually is something which is called the deterministic behavior, where the particles and the motions and everything is quite deterministic. Then comes Albert Einstein, who ushered a new era of relativistic physics, which is more or less relativistic in behavior. And then we call quantum physics primarily with the name of Erwin Schrödinger, and this calls the quantum behavior of particles. Now, physicists always strive not to have separate theories, but somehow unify and make a comprehensive theory so that everything is explained at one go. So all these theories, deterministic, relativistic, and quantum physics, would be united into a common theory. And this would help us to understand nature, physics, space-time, behavior of subatomic particles from the microcosm to the macrocosm much better. So this actually shows the reason that why we need a unified field theory. So classical physics, which is predominated by Newton's laws of motions, and then comes the relativistic physics, which is divided into two parts: the special relativity, which is predominated by the famous equation of E equals to mc squared, and the quantum physics, which talks of Heisenberg's uncertainty principle. But the relativistic physics on the general theory of relativity is this one, which is called Einstein's field equation. If you really want to dig much more deep in understanding the general theory of relativity and Einstein field equations, I've got quite a big series of videos explaining this. Anyway, so let us come back to what we were discussing. Now, if you see these three ways, I mean to see the three ways in which nature has described. So general theory of relativity and quantum physics has been united, or we are trying to unite into something which is called a string theory. So it is one of the unification theories. If you want to know again about string theory, I've got 2-3 videos on the basic introduction. However, classical physics, which deals with the Newtonian part, along with relativistic physics, we will take only the special relativity in case of quantum field theory, and quantum physics. Together, they make up what is called quantum field theory. So the unification theories are quite a good number in which is available, which physicists are thinking. But here we are primarily concerned about special relativity, classical physics, and quantum physics. And string theory is trying to unite general relativity and quantum mechanics. Quantum field theory has already united and has got a big success. So string theory, as I was discussing, it is general relativity for quantum mechanics. So it is a marriage of a very big with very small. But yes, quantum field theory unites special relativity, classical field theory, and quantum mechanics. And there are two parts, two types of quantum field theory, which we will definitely look into it. One is called quantum electrodynamics, which is abbreviated as QED, and one is called quantum chromodynamics, which is abbreviated as QCD. So what we get from here is that to describe all fundamental forces and the relationship between elementary particles in a single theoretical framework, so unified field theory is a theory that allows us that it is usual though of fundamental forces and elementary particles to be written in terms of pair of physical and virtual fields. Also, according to the modern discoveries in physics, forces are not transmitted directly between interacting objects, but instead they are interrupted by intermediate fields, as we just saw that it is a field which is propagating amongst us. And don't worry, we will see more about field and how the concept of field changes. Okay, so up till this part of the video, I would like to tell you that we learned about a basic understanding of quantum field theory, and now we saw that why do we need a unified theory. And currently we are dealing with quantum field theory, which is QFT, which is one of the part of the holistic approach of unified theory, and string theory, and there are many other theories which is trying to unite gravity along with it. But in this video we won't be considering gravity, but take into special relativity, quantum mechanics, and classical physics. Now it is so far so good, but the thing is that first of all we need to understand that why do we need and from where the quantum field theory emerged, and that I'm going to explain in the next part of the video, how it all started, a chronology of development. So have a cup of coffee, sit back, relax on your sofa, because I will be taking you through a wonderful journey of physics and the history of science, the development of quantum field theory. The earliest possible, I would say, successful classical field theory is one that emerged from Newton's law of universal gravitation, which he has described during the pandemic time, which was persisting in England during this time, the Great Plague. And during that Great Plague, he covered a great topic, that is in 1687, a treatise on Philosophiae Naturalis Principia Mathematica. The force of gravity, as described by Newton, is an action at a distance, and it affects faraway objects. In a letter to Richard Bentley, Newton writes, "It is inconceivable that inanimate brute matter should, without the meditation of something else which is not material, operate upon and affect other matter without mutual contact." So you see that the letter actually persists in a very naive way. What Isaac Newton tells, that inanimate brute matter should, without the meditation of something else, operate upon, and he expresses his doubt. So the thing is that what he tried to call is as action at a distance. Its effects far away objects are instantaneous, no matter the distance. Now, it was not until the 18th century that mathematical physicists discovered a convenient way to describe gravity based on fields, a numerical quantity which we call vector in case of gravitational field, which assigns to every point in space, indicating the action of gravity on any particle at that point. Dating back from Isaac Newton, we now have to go back to another great person, Michael Faraday, one of the greatest experimental physicists I should consider. And he left school at the age of 14, and he essentially knew almost no mathematics, yet rather wonderfully built upon this intuition for the way the universe works. That meant that he really made one of the most important contributions to theoretical physics. Over a period of 25 years, he was playing with the idea of electricity and magnetism. And he first coined the term field. So he was getting magnets and wrapping copper around them, and he was playing. So let me show you an example. Now, if you take a couple of bar magnets and you push them together so that the North Pole approach each other, and the experiment is being well done. And as you push these magnets together, you will feel this spongy kind of a force that is pushing them apart. Now, during that time, Michael Faraday made a very bold proposal that there was actually something in between the magnets. Right. So Faraday said that there was something in between the magnets, and it is just a thin layer, but there is clearly something, and he called it as a line of force. And later he recounted that not only are there particles in the universe, but in addition, there is this other kind of object, a very different kind of object, a field, which exists everywhere in space all at once. So you see, the first coining of the term field came from Michael Faraday, which Isaac Newton wrote in a letter to Richard Bentley about some kind of a fictitious force which is acting something at a distance. Right. So, and he also told that these fields are real. Now, dating back from Michael Faraday, we now need to go to this person, James Clerk Maxwell, and actually Maxwell's electromagnetism was completed by around about 1864, which described the relationship, these famous equations of Maxwell. Again, if you want to know more about Maxwell's equation, I've got an entire playlist describing each and every component of Maxwell's equation from Gauss's field and everything. So anyway, so the thing is that the relation between electric field, magnetic field, electric current and electric charge was quite well established. Maxwell's equations implied the existence of electromagnetic waves, and these electromagnetic waves are phenomena whereby electricity and magnetic fields propagate from one spatial point to another at a finite speed, which turns out to be the speed of light. So you see that as we move ahead, the concept of field changes, and the existence of electromagnetic waves, that means electricity and magnetism, they are propagating from one point to another at a finite speed, that is the speed of light, and thereby we put an end to the elusive concept of action at a distance, and thus we refute it. Now, we saw this is the classical era, which is covering all those things, but now we come to what we call a quantum era, and there is a paradigm shift, not only in terms of technology, mathematics, but also in terms of human thinking. Now, in spite of the enormous success of classical electromagnetism, we were unable to account for the discrete lines of atomic spectra, and we cannot also tell the distribution of black body radiation in different wavelengths. So these were the two problems that still persisted, and mathematics or physicists were unable to explore. And it was Max Planck's study on the black body radiation marked the beginning of what we call the era of quantum mechanics. Now, he treated atoms which absorb and emit electromagnetic radiation as tiny oscillators, yes, quantum harmonic oscillators, with the crucial property that their energies can only take a series of discrete rather than continuous values. So this is what is called quantization, right? So these are known as a quantum harmonic oscillator. This process of restricting energies to discrete values is known as quantization. Now, based on Planck's idea, the great Dr. Albert Einstein proposed in 1905 that an explanation for the photoelectric effect, that light is composed of packets, energy called photons. This implies that the electromagnetic radiation, while being in the waves in classical electromagnetic fields, also exist in the form of particles. So this equation Ek is equals to h nu is something which comes obviously from the photoelectric effect. So the problem of not being able to define atomic spectra and black body radiation are slowly being taken over with Max Planck's discovery of quantization and Albert Einstein's equation on photoelectric effect. So we move now into the era of 1913, when Niels Bohr introduced the Bohr model of atomic structure, wherein electrons within atoms can only take a series of discrete rather than continuous energies. So this is another example, remember, of quantization. Bohr model successfully explained the discrete nature of atomic line spectra. So you can see on the left hand side the increasal orbital energy from K to L to M and N and so on. Now let us not forget about this great Italian scientist Louis de Broglie proposed the hypothesis of wave-particle duality with this equation, which you can see right on your screen, that microscopic particles exhibit both wave-like and particle-like properties under different circumstances. So you see, what we are now venturing is that the stage is slowly getting set for quantum mechanics. Now, these ideas were quite scattered during that time. Broglie's idea, de Broglie's idea, Bohr's atomic model. So we need to unite, and that is what exactly happened. So uniting these scattered ideas into kind of a coherent discipline, if we see the timeline of quantum mechanics from 1819 to 1940, then we see that the time between 1925 to 26 is the best, and we can consider this to be a golden era. And with the contributions from Max Planck, Louis de Broglie, Werner Heisenberg, Max Born, and when Schrödinger, Paul Dirac, and Wolfgang Pauli, it got something of a much more robust mathematical formulations. So in the same year, remember that Albert Einstein published his photoelectric paper, and Einstein's special theory of relativity was built on Maxwell's electromagnetism, which we just saw. So new rules were framed. Obviously, Lorentz transformations were given for the time of space and coordinates of an event changes under changes in observer's velocity, and the distinction between time and space was blurred. So this is an era of quantum physics, era of quantum mechanics, when everything was changing. Along with that, there were certain new areas in physics and mathematics which started creating problems. Okay, so now we enter into the time when we need to understand why quantum field theory emerged. I'm going to say every physics theory or mathematical theory or concept you will see emerges out of certain problem, out of certain issues which the current theory cannot solve. So quantum field theory emerged out of a problem, and we will now look into what is the problem, and that is the reason of the QFT's emergence into physics. Okay, so you can quickly understand what this equation is all about. This is the Schrödinger's equation, which is the underlying, I would say, the heart of quantum mechanics. Now remember that Schrödinger's equation of quantum mechanics could explain the stimulated emission of radiation from atoms, but where an electron emits a new photon, but it was unable to explain the spontaneous emission. Now, obviously, the question would be, what is spontaneous emission? I'm coming to that. Now, spontaneous emission is something where an electron spontaneously decreases in energy and emits a photon without the action of an external electromagnetic field. Right. So, a subatomic particle transits from an excited energy to a lower energy and emits a quantized certain amount of energy in the form of photon. So if atoms or molecules are excited by some means of heating, then obviously it is called luminescence, for example, fireflies. Okay, now let us look into what we call is a spontaneous emission, and then only we can understand the problem. Okay, so if I get a kind of an electron which has got a high energy level, and we just mathematically we try to mention it as E2 as the excited state of energy, it must spontaneously decay to a lower state, which we maintain it as the ground state, or we call it as E1. Now, releasing the difference in energy between two states, what it does, it releases a photon, as you can see on the figure right now. Now, the photon obviously will have an angular velocity, frequency, and an energy which will be E2 minus E1 equal to h bar, which is the reduced Planck's constant. Now, remember that if the excitation is affected by the absorption of radiation, the spontaneous emission is called fluorescence. Sometimes molecules have a metastable level and have a continuous fluorescence. So, spontaneous emission of excited then heating is what is called also luminescence. And if it is excited by absorption of radiation, then it is called fluorescence. These are just examples. Now, spontaneous emission cannot be explained by classical electromagnetic theory, and it is fundamentally a quantum process. Now, according to the American Physical Society, the first person to correctly predict the phenomena is in front of you, none other than Albert Einstein, and in a series of papers in 1916, which is now called Einstein coefficient, which is denoted by this A21. Now, Einstein's quantum theory of radiation anticipated ideas later, which developed into quantum electrodynamics. Later, after the formal discovery of quantum mechanics in 1926, Paul Dirac actually, formulated in quantum theory radiation, which is actually a kind of a precursor to quantum electrodynamics. Okay, so we are in a position where we can now understand that what is spontaneous emission. I will show you further examples and illustrations. So it goes from high energy to low energy and releases a photon. Okay, so this the Schrödinger equation, which you can see right on the screen, here the electron's energy level is quantized but electromagnetic field is not quantized, right? And what we can see is that if the excited state of atom from E2 level, the excited state of atom cannot decay to the ground state. In the absence of the quantized electromagnetic, because we have not quantized electromagnetic field, the excited state of atom cannot decay to the ground state. In order to explain spontaneous transition, quantum mechanics now needs to be, so this wave, electromagnetic wave, for that, yes, electromagnetic waves needs to be quantized at every point in space. Okay, so what is happening is that now it is a time that the quantum mechanics, the mathematics or the concept of quantum mechanics must be extended to what we call quantum field theory, QFT, that the electromagnetic field is quantized at every point in space. So I hope this is quite clear, because if you're not clear on this, you can pause and take a note of that, or try to understand that the quantization in terms of electromagnetism at every point in space was necessary. And if you look a little bit deep into Schrodinger's equation, it is basically the Hamiltonian, and it is one way the classical, it is basically the classical concept of a classical classical theory. So if Schrodinger's equation takes place in terms of classical theory, not literally, then obviously it won't consider the quantization. So hence it is unable to describe what is called spontaneous emission. Now, if I consider quantum electrodynamics, we have not although covered, we will cover it, but just let us assume the electromagnetic field has a ground state, right? E2, the high energy level, and it has got a low energy level, and there is something which is called a quantum electrodynamics, QED vacuum, which can mix with the excited stationary states of the atom. Now, you see that this for this quantum for the electromagnetic wave quantized at every point in space. For E2, and if I take further E1, then when it moves from E2 to E1, it also emits and a kind of a photon. So what we can say is that the electromagnetic field mixes with the transition of the electromagnetic field from the ground state to an excited state. So here it is, and here from here it goes, and it also releases a photon. Okay, so when I would like to say, you see what happens here is that from when electron is transitioning from excited state to a ground state or low energy state, there are many ways, there is only one way in which it releases a photon, that is, it has got only one electron transition. But in that case, if I take an electromagnetic wave in the classical sense, when it goes from high energy to the ground state and releases the photon, it has infinitely many degrees of freedom. Right? It has got many degrees of freedom, and we can say that the phase space offered by the electromagnetic field is infinitely larger than that offered by the atom. Obviously, as you can see on the left hand side, the atom has only one electron transition, and it has got infinitely many degrees of freedom and many ways of transition. Now, this infinite degree of freedom for the emission of the photon results in the apparent irreversible decay, which causes the spontaneous emission. So, the question arises that can we find a theory which would quantize electromagnetic field, thereby describing the classical electromagnetic field as well as the emission of photon by an electron dropping into quantum state of lower energy. Right. So, you understand the problem that we are facing, and this actually is the emergence or the real cause that quantum field theory would come in. So the question is that now can we find out something, because here we get infinite many degrees of freedom, infinity is a lot of problem. Now before going into this, the answer, I would like to take a step back, because this is important, and I would like to clear out a very important concept which is called quantum electrodynamics and quantum chromodynamics, QED and QCD. In a very simple language, I would like to tell you that quantum field theory is actually divided into two parts. Okay, so quantum electrodynamics, which is the relativistic quantum field theory of electrodynamics, and quantum chromodynamics. So here it says that it describes how light and matter interact, and is the first theory where full agreement between, and this is the theory where the strong interaction between quarks mediated by gluons take place, right? So in a sense, because it describes how light and matter, so obviously for light and matter we have to take special relativity into account. So what we can say from here is that it was Paul Dirac who first mathematically described all phenomena involving electrically charged particles interacting by means of exchange of protons, and represents the quantum counterpart of classical electromagnetism. So it was Paul Dirac, so he was able to compute the coefficients of spontaneous emission of the atom, and the first theory, which is in full agreement between quantum mechanics, and there is no discrepancy, no doubt, with special relativity. Whereas quantum chromodynamics is a type of quantum field theory which is called a non-abelian gauge theory with symmetry group SU3. Now remember that for the sake of this video, because we are just covering up the concepts of quantum field theory, we won't consider quantum chromodynamics. If you really want, let me know in the comment section. I will make a separate video on quantum chromodynamics. Quantum chromodynamics is the theory of strong interaction. Quarks are fundamental particles that make up composite hadron, such as the proton, neutron, and pion. Now, so the history of quantum field theory, which we are learning right now, starts with Paul Dirac, because he was the first who attempted to quantize the electromagnetic field in the late 1920s. The question is that whether he was able to achieve it or not, we will cover up in the next part of our video. Okay, so let us see quickly what is the difference between QED and QCD. I'm not reading it out. You can just take a note of that. Understand that quantum electrodynamics basically is fundamental interaction between charged particles, and quantum chromodynamics describes interaction between the quarks and gluons. And there are certain colors, etc. Quite a complicated part. I will cover up in the next part of the video. So here you can pause and take a quick snap if you want to take a break, etc. because more intense things are coming up. So this is what quantum electrodynamics and QED and QCD is all about. Now we come to what we were telling, that whether we are able to construct a theory which would explain. So now we will go ahead and explain QED and what it is all about. So quantum, I would say electrodynamics is basically a theory which is in full agreement with quantum mechanics and special relativity. It is the first formulation which was done by a famous Paul Adrian Maurice Dirac, which explained spontaneous emission. Remember, spontaneous emission was something that we are stuck into. It also has something which is called a creation and annihilation operators. I will just take a quick note on this. Creation and annihilation operators are mathematical operators that have widespread applications in quantum mechanics, right? So an annihilator operator, which you can see A with a hat on the top, lowers the number of particles in a given state, and a creation operator with a dagger on the top with a hat is a one which increases the number of particles in a given state, and it is the adjoint of the annihilator operator. So just a quick note on that. And Feynman explained two different Feynman diagrams. So now you see it was basically with the joint effort of Eugen Wigner, Pascual Jordan, Heisenberg, and Enrico Fermi that a more robust mathematical structure was ultimately given. So this is what quantum electrodynamics is all about, and this is how we address the spontaneous emission problem. Okay, now I would like to show you a very interesting thing. Now let us consider the left hand side to be time. Let us consider the right hand side to be space. Now if I take 2 points A and B, and if I consider one photon moving, then it would certainly go like this, the wiggling line, right? And then I consider this is the photon, 2 points C and D, and here is a straight line which is going, and this is the electron. And now I take a combination of these two, and here it where it meets. Now what I just showed you is a very simple illustration of quantum field theory through Feynman's diagram. So the emission or absorption of a photon by an electron is depicted by this. So here you see that what Feynman told is simple three states. A photon, which is this wiggling line, first on the left, goes from one place to another. An electron goes from one place to another, and an electron emits or absorbs a photon at a certain time. Right. And he further, what he did is that Feynman is mostly credited for that famous Feynman diagram, obviously. Now, it implies a complex computation for the resulting probability amplitudes, which we know is the heart of quantum mechanics, but provided it is the case that the more complicated the diagram, the less it contributes to the result. So if, that is called probability amplitude. So this is the basic approach for quantum electrodynamics to calculate the probability of an interaction between electrons and photons. So if you take that, for example, there is one place when it is moving from point A to point B, we will write like this, P A to B, and if an electron is moving from point C to D, we write it in this way. Right. So, but remember that there is an infinite number of other intermediate virtual processes in which more and more and more photons are absorbed or emitted. For each of these processes, a Feynman diagram is dedicated. This implies a complex computation for the resulting probability amplitudes, which we just have shown. Okay, so quantum electrodynamics, if you take it in a very layman's term, it is based on the assumption that is complex interaction of many electrons and photons can be represented by 1, 2, 3. We just have seen that and how it is depicted in the diagram. And using the probability amplitudes to calculate the probability of any such complex interaction, we squared the total of the probability amplitudes, and if an event can happen via a number of indistinguishable alternative processes, then its probability amplitude is the sum of the probability amplitudes of the alternatives, and if a virtual process involves, then it is the product of the component of the probability amplitudes. Right. Okay, now that we have understood that quantum electrodynamics is actually giving a solution to the spontaneous emission problem, etc. Still, there are certain problems which exists, and these are called infinities and divergence. And let us see in the next part of the video that what could be the possible solution. Okay, now it was Paul Dirac who in 1927 coined the term quantum electrodynamics, and he successfully explained the phenomena of spontaneous emission. Now, according to the uncertainty principle in quantum mechanics, quantum harmonic oscillators cannot remain stationary. So here is the uncertainty principle. Because they cannot remain stationary, they have a non-zero minimum energy and always must be oscillating, or can just imagine that it's going up, down, left, right. It is always oscillating. Why? Because it cannot remain stationary because of the uncertainty principle, right? So therefore, even in perfect vacuum, there remains an oscillating electromagnetic field having a 0 point energy, and it is this quantum fluctuation of electromagnetic fields in the vacuum that stimulates the spontaneous emission and radiation between electrons and atoms. Obviously, during that time, we are talking of 1927 and so, Dirac's theory was hugely successful in explaining both the emission and absorption by atoms. So it explained both the emission and absorption. By applying a second order perturbation theory, it was able to account for the scattering of photons, resonance, fluorescence, and non-relativistic Compton scattering. So this was a big success in terms of explaining, I would say, spontaneous emission, the non-relativistic Compton scattering, and everything. But here comes a problem which started to crop up, started to boil. Okay, so before going into that, I would like to give you a very quick overview. What is Dirac equation and what does it mean? Don't worry, we're not going to delve much more into the derivation part. So the Dirac equation, something looks this or this. It describes all the spin-half massive particles, right? Second, it is consistent. Both quantum mechanics and special relativity, obviously if light etc. is coming, we have to take special relativity, and it is quite well validated through experiments of hydrogen spectrum. Now, what does it say? I mean to say, if you say that what is a Dirac equation, not those huge equations, what does it say? It says that it is basically the relativistic counterpart of the Schrödinger equation applicable to spin-half particles. Now you can go back again to this video and see that Schrödinger's equation, which was unable to quantize electromagnetism, I mean to say classical electromagnetism at every point in space, is now being replaced, I would say, is being extended by Dirac equation because it is the relativistic counterpart. Also, the purpose of formulating this equation was to study the relative motion of the electron and treat atom as consistent with relativity. Here you can see the c, which is the speed of light, and I will make a separate video Dirac equation explaining everything, what is mu, nu, and this I, h bar, and the partial derivatives. So in general, what I can tell you is that this is what Dirac equation, it takes into account special relativity as well as quantum mechanics. It is well validated, and it now treats the electron as consistent with relativity. But as I was telling, there were certain problems which were ensuing, and these are the problems with infinities. Now, it was Robert Oppenheimer who showed in 1930 that that high order perturbation has got some problem. So the self energy of the electron, then the energy shift of electron states, these are creating a lot of problems. So these would lead to infinity and divergent conditions, which all the physicists and we do not want to encounter because we want to measure something. So here comes Oppenheimer. I was just telling that in 1930, high order perturbative calculations in quantum electrodynamics resulted in infinite quantities such as the electron self energy and the vacuum 0-point energy. Now it was then through a series of papers, this gentleman Ernst Stuckelberg between 1934 and 38 published a relativistically invariant formulation of quantum field theory, but somehow unfortunately in 1947 it was rejected by the Physical Review, but Stuckelberg also independently developed a complete renormalization procedure. We will come to that. What do we mean by renormalization? So the problems with infinities have started. Facing this problem, John Archibald Wheeler and Heisenberg proposed in 1937 and 1943 what is called an S-matrix theory. Now again, the question is that what is S-matrix theory? I will just give you a simple example. Now, if there are two particles, say for example, which are colliding against each other, and there is a collision, then the S-matrix theory would give the likelihood of its possibility. So it's a kind of a mathematical, we can say it is a kind of a mathematical framework which accounts into the likelihood of each of the possibilities. So here it is, an array of mathematical quantities that predicts the probabilities of all possible outcomes of a given experimental solution. So since the specific details of microscopic interactions are inaccessible to observation, the theory should only attempt to describe the relationships between a small number of observables, which is the energy of atom. Now in 1945, Richard Feynman and Wheeler daringly suggested just to abandon quantum field theory. It is nothing happening, so let us abandon together, and it is proposed that it is just an action at a distance as a mechanism of particle interaction. So you see that the S-matrix theory was not quite successful, and these people have started. But we should not stop, isn't it? How can we abandon a quantum field theory which is so elegant in nature? And the breakthrough came here around 1950, when a much more robust method for eliminating these infinities, these problems, was given by Julian Schwinger, Richard Feynman, Freeman Dyson, and Shinshiro Tomonaga. Among them, Julian Schwinger, Richard Feynman, and Shinshiro Tomonaga has won the Nobel Prize in Physics. So the main idea is to replace the calculated values of mass and charge in finite though may be by finite measurements. So here it is. To replace the calculated values of mass and charge by finite measurement. And this is done what is called renormalization. We will soon see in details what is the renormalization. So this systematic computational procedure actually can be applied to arbitrary order in perturbation theory. Now, at the same time, an elegant formulation came from Richard Feynman, introduced what is called the famous path integral formulation. So, when you go from one point to another, electrons take numerous paths. So, the latter can be used to visualize this one. Each diagram can be interpreted as path of particles in an interaction, with each vertex and line having a corresponding mathematical expression, and the product of this expression gives a scattering amplitude of the interaction represented as I showed you in this diagram. Okay. So now we come to know that what is renormalization. So we first went into spontaneous emission. The problem was solved by Paul Dirac. Then comes the infinity problem. It is further again solved by renormalization. Okay, we will now see what is renormalization. Okay, so simply stated, it removes infinities. So renormalization is a mathematical method to remove infinities and to obtain a finite answer. Simple. Renormalization is a collection of techniques. This to treat infinities arising in calculated quantities by altering values. So you can just read this. This is just a kind of a clear example in a simple plain English. So now what I would like to show you is that the things we call electrons and the things we call quarks are not actually themselves as fundamental objects. Instead, there is spread throughout the entire universe something which is called an electron field, a positron field, and a neutrino field, right? Exactly like the electric and magnetic fields we know. And the particles of these we call electrons, are just nothing but they are ripples of the field. Imagine a pond throwing a kind of a stone and it's creating a ripple. And the same is true for any other particles that we mention. So there is a quark field. In fact, there are 6 different quarks, and there is a Higgs boson. So something like that. Okay, so I would like to show you how the problem arises and what actually renormalization does. So let us say that we have an electron here. We've got a mass m and a charge c. And this is actually interacting with photons. It is interacting with positrons and many other fields. It's a cloud of things. And now when it comes out after interaction, we get a kind of a totally different mass. I just mentioned it, n plus plus, cd minus minus. What I'm trying to tell you is that when it interacts with certain other particles, virtual particles in this cloud, the electron's mass and the entire thing changes. And that is what exactly renormalization does. So renormalization replaces the initially postulated mass and charge of an electron with experimentally observed mass and charge. So this is an example that positron and more massive particles like protons exhibit precisely the same observed charge as the electron, even in the presence of much stronger interactions and more intense clouds of virtual particles. So this is what I am trying to show you, that the electron, when it interacts and it eventually leads out to certain different mass and charge, it actually exhibits the same observed charge if you apply renormalization, and even in the presence of a much kind of a stronger, I would say, clouds of interactions. So you see, this diagram shows that simple electron and photon have become so complicated. So in order to remove these infinities, we have to modify the relativistic quantum field theory, and the most popular method is by doing the path integral formulation. So calculating this type of diagrams involves performing integrals. Some of these integrals diverge, which is not a very good thing. So how do we do? The first step in renormalization is what we call regularization, which you all know, where we modify the theory in such a way that the divergences disappear. The second stage is taking a parameter, that means control the amount of modification and sending it to 0, taking a careful limit. If it is done in a proper fashion and the theory is renormalizable, we make all the divergences from all the possible loops disappear, and thereby we establish in quantum field theory a system where all infinities and divergences vanish, provide us a complete, robust system. So finally we understood, and here we are. We have ended the war against infinities. It has come to an end. We established the quantum field theory, taking care of the problem that arose, and most importantly, the quantum field theory is now established, and it was with the invention of renormalization procedure and Feynman diagram that quantum field theory arose as a complete theoretical framework. That's all for today's video. I know it is long, but I have to explain the entire process because quantum field theory indeed is intense. So here is a summary of what we learned today. What is quantum field theory? The problems and the need for quantum field theory. A brief history, development of ideas, emergence, paradigm shift, the problems with Schrodinger equation, difference between QED, QCD, how QED is performed, challenges and problems in QED, and the renormalization and dissolution. So here is before you a kind of a basic layman's idea how quantum field theory emerged, history, the people, the failures, the success which are involved. I think you have enjoyed it. Please do let me know your comment. Please do subscribe to my channel Physics for Students and click on the bell icon and click on all to get all the notifications from Physics for Students. This is Shaunak signing off from Physics for Students. I just want to come back with yet another interesting video as I always do in physics and mathematics. Thanks for your participation, but do let me know how do you like and what are your ideas about this video on quantum field theory. Thank you very much. Wishing you a great day ahead. Goodbye, take care, and may God be with you.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.